Hello students, this is part 3 and the last part of Organic Chemistry Lesson 1. Now, let's discuss about ground state electron configuration. The ground state electron configuration is the arrangement of electrons around the nucleus of an atom with lower energy levels. The electrons occupy the orbitals of varying energy levels naturally falls toward the lowest energy state or ground state. Electron configurations are written using the principal quantum number n, followed by the orbital s, p, d, or f, with a total number of electrons written as the superscript. So, if you recall your chemistry classes in senior high school or junior high school, you are taught how to write electron configurations. And I know some of you may be confused. How are we going to write them in sequence, or how do you get 1s2, 2s2, 2p6, and so on and so forth? So you're going to learn that here, or review your prior knowledge about ground state electron configuration in this class. Okay, actually there are 3 principles that we are going to follow in writing our ground state electron configuration. The first one is the alphabet rule. So rule 1, follow the alphabet principle. And the second rule, we have the Polyexclusion Principle. And the third rule, you have to follow the Hund's rule. Okay, so let's discuss alphabet principle first. Alphabet principle states that in the ground state of an atom or ion, electrons feel subshells of the lowest energy or lowest available energy. Then they feel subshells of higher energy. So what does it mean? You have to feel the subshells with electrons starting from the lowest available energy, okay, before you go to the subshells of higher energy. So for example, the 1s subshell is filled before the 2s subshell. Now, this is the pattern on how are we going to write the correct ground state electron configuration. So according to alphabet principle, we have to start with 1s first and then down to 2s. Then after 2s, the next is 2p. Then 2p down to 3s. Then from 3s, the next is 3p. Then from 3p, okay, down to 4s. And then from 4s, okay, up here in 3d. Okay, so let me just clarify this one. You will ask me, Miss Dizon, why is 4s written first before 3d? Why do you think so? Because 4s, okay, has the s orbital, while 3d d orbital, and s orbitals have lower available energy, while the d orbitals have higher available energy. So that is the reason why 4s is written first before 3d. Okay, so please do not get confused. So let's go back from the top. From 1s down to 2s. Then from 2s, next is 2p. Then from 2p, we will go to 3s. Next to 3s is 3p. Then next to 3p is 4s. Okay? And then after 4s, you will go up to 3d. Okay? Is that understood? And then from 3d, okay, look at that one, you will go to 4p. And then next to 4p, you will go to 5s. Okay? And so on and so forth. So that is the pattern. From 1s, 2s, 2p, then down to 3s, okay, and then 3s to 3p, and then down to 4s, and then up, okay, going up, you will write 3d, okay, and then from 3D down to 4p. And then 5s. Next to Aufbau principle is the Polyexclusion Principle. The Polyexclusion Principle states that no two electrons in the same atom can have identical values for all four of their quantum numbers. In other words, no more than two electrons can occupy the same orbital, and two electrons in the same orbital must have opposite spins. So let me just clarify this one. In the previous lesson, you have seen that an orbital shell, okay, is occupied by a maximum of two electrons, and electrons are represented by arrows. If you have noticed, the arrows are in opposite spins. So one arrow is facing upwards and one arrow is facing downwards or pointing downwards. Okay, it says here in number 1, no more than two electrons can occupy the same orbital. So in one orbital, the maximum electron is always 2. Okay, so now if we have a box here, that will be your orbital diagram. So for this one, the one with just one line, now you call that the illustration for orbital shell. Now for this box, you call it orbital diagram, and yes, it's just the same with orbital shells, only it is displayed as a box. And in one box, okay, or in one square, there are also two arrows. And again, the arrows represents the electrons, which are pointing into opposite spins. Okay, so they are pointing into opposite direction. One pointing upwards and one pointing downwards. And that's what you mean by Polyexclusion Principle. Okay, now look at this one. This illustration here, that is correct, right? Because in one box or one orbital diagram, it only contains two electrons, okay, pointing or having opposite spins. Now look at this one. Why do you think it has an X mark? It has an X mark because this representation or illustration is wrong. Look at the direction of the arrows. They have the same direction of the spin. Okay, the two arrows are pointing upwards, and that is not right. Okay, so automatically that is wrong. I hope you get the concept of Polyexclusion Principle. Okay, just remember, for each orbital or orbital shell or in orbital diagram, okay, there is only a maximum of two electrons. Okay, and then the arrows must have opposite spins, or electrons must have opposite spins, and electrons are represented by arrows. Yeah, I hope you get that one, class. Now let's proceed to the next, the Hund's rule. Hund's rule states that every orbital in a subshell is singly occupied with one electron before any one orbital is doubly occupied, and all electrons in singly occupied orbitals have the same spin. So what do you mean by that? We have the empty orbitals right here, the singly filled orbitals right there, and the doubly filled orbitals right here. Okay? It has been mentioned in Hund's rule that every orbital in a subshell is singly occupied with one electron before any one orbital is doubly occupied. So you have here your empty orbitals, right? And then Hund's rule would like you to plot the electrons one by one first for each orbital subshell. And then if there is a remaining electron, then that is the time that you will fill in. So that makes them doubly filled orbitals. Okay, so let me show you an example. For example, we have an atomic number of 7. Okay, 7. So we have here the 1s orbital, and we have let me illustrate that correctly. We have 1s, 2s, and then 2p. This is 2p. So we have an atomic number of 7. And that means we also need to plot 7 electrons. And remember, we will use arrows in filling in the electrons because arrows represents the electrons. Okay, say for example, this is our orbital subshells, the 1s, 2s, and 2p. So in Hund's rule, we have to distribute the electrons one by one first. So we have 7, so 1, 2, 3, 4, 5. Okay, we have plotted 5 electrons already. Now, 7 minus 5 electrons, then there are 2. So we only need to plot 2 electrons more. So 5, 6. And this is the time that we are going to use the arrow pointing downwards. And then 7. So 1, 2, 3, 4, 5, 6, 7. Look at 1s and 2s. Okay? If you have noticed, these orbitals are doubly filled orbitals, right? While 2p, okay, look at 2p, singly filled orbitals. Why is that so? Because we follow the Hund's rule. You have to distribute the electrons first before going back to 1s to fill in the remaining electrons so that they will be balanced. Now, how are we going to write the electron configuration? So from that, following our illustration, we have one. Oh, I'm sorry. Let me erase that one. Okay. So we will have 1 S2 and then 2 S2 and 2 P3. So did you notice our superscripts right there? Okay, those superscripts represents the electrons, okay? The electrons for each orbital levels or orbital subshell. So in 1s there are 2 electrons, so that's why we write 1s2. And for 2s, look at that one. How many electrons do you have there? You have 2. That is why you will write 2s2. And then we have 2p. How many electrons do you see? You have 1, 2, and 3. That's why you will write 2p and 3. Okay, 1s2, 2s2, 2p3. And how many electrons do we have from the start? We have 7, so let's count. 2 plus 2 is equal to 4. 4 plus 3 is equal to 7. Did we do it right? Of course, yes. Oh, please remember that it's very important to follow the alphabet principle, the Polyexclusion Principle, and the Hund's rule. For the alphabet principle, you will have a guide on the pattern. Okay, what comes next after 1s? What comes next after 2s? And so on and so forth. And we also have the Polyexclusion Principle. So in the Polyexclusion Principle, we were told that in each orbital, okay, it will only contain a maximum of 2 electrons, and the electrons must have opposite spins. And remember, the arrows represent the electrons. Okay, and for the Hund's rule, let me just repeat. You have to distribute the electrons first. Okay, distribute them one by one in each orbital level or in each orbital subshell before you're going back to 1s to fill in the remaining electrons. Okay, so in our example, we have 1s2, 2s2, 2p3. And the superscripts, like these 2, 2, and 3, they are the electrons representing for 1s, 2s, and 2p. Okay, I hope that is clear. Okay, so it's just the same for my example. Look at this one, class. So I got this right. And this is wrong. Then my example here and the example here is the same. So look, I have the same solution. 1s2, 2s2, and 2p3. Hey, don't do this. Don't do the second one. Don't do this. Why? you will have an empty orbital, and it should not be empty. Okay? It should not be empty. So that is why it's very important to follow the Hund's rule. So all orbitals will have electrons because you distributed them equally. You distributed them one by one before going back to 1s and fill in the remaining electrons. Okay? So please do not forget Hund's rule. It's very important to follow that one. And yes, you also have another example here. Okay? Some examples of how these rules apply are shown in table 1.1. We have hydrogen, for instance, has only one electron, which must occupy the lowest energy level, lowest available energy. So we have hydrogen here. The atomic number is 1. Therefore, the configuration is 1s1, okay? 1s1, because it only have one electron. Hydrogen has only one electron, okay? And for the carbon, okay, for the carbon, it has 6 atomic number. Therefore, how many electrons? Okay, you also have to plot 6. So we also have phosphorus, okay, atomic number 15, okay. However, I think there is a mistake in carbon. There is a mistake in plotting the electrons here because there is an empty orbital and it should not be empty. So let us correct that one. Let us correct carbon. We have 1s, 2s, then 1, 2, 3, 2p. And how many electrons do we need to plot? We have 6. Okay, well, let us use a different color. 1, 2, 3, 4, 5. Now we have plotted 5 electrons. So how many remaining electrons? Only 1. Then we have 6. So what is the correct electron configuration now? So it should be 1s2, then 2s1, and 2p3. Okay, again the superscripts represents electron. We have 2 electrons in 1s, 1 electron in 2s, and 3 electrons in 2p. So 2 plus 1 is equal to 3. 3 plus 3 is equal to 6. Okay, so that is the one. Alright, so we have a worked example right here. Give the ground state electron configuration of nitrogen. So it's already shown in this example. Okay, in this example, 1s2, 2s2, and 2p3. So you just please read this by yourself. And let me just read this one before we end this video discussion. So you have there your strategy. Find the atomic number of nitrogen, which is 7, to see how many electrons it has. And then apply the 3 rules. Apply the Orbital principle, Polyexclusion principle, and the Hund's rule to assign electrons into orbitals according to the energy levels. And then nitrogen, right, after referring to the periodic table, you will see that it has an atomic number of 7, and thus it has 7 electrons. The first 2 electrons go into the lowest energy orbital, or 1s2. The next 2 go into the second lowest energy orbital, which is the 2s2. And the remaining 3 go into the next lowest energy orbital, 2p3, with 1 electron in each. Thus, the configuration of nitrogen is 1s2, 2s2, and 2p3. But you can also go back in this example. I have shown you here how to draw and how to write the correct electron configuration while applying the Orbital, the Poly, and the Hund's rule. Okay, so that ends our lesson 1. I hope you've learned a lot. Now that we're done with introduction to organic chemistry and atomic structure, you will be required to do the learning activity 1 and take the first practice assessment. Okay, stay determined and you can do it. Thank you very much, students, for watching this video. Goodbye!